Hello guys. I'm happy that you joined in this workshop provided by Code Labs Academy. It's about gradient descent with JAX. So, if you know nothing about gradient descent or you know nothing about JAX, that's fine because this workshop is made for beginners. So you'll get your hands wet with JAX and the new concepts. And yeah, it will be like an initial point for you in your learning path. So without further ado, let's start. Let me just pick the laser point. All right. Can you confirm that everything is fine? You can hear me and you can see my screen? Good, perfect. So yeah, let's start. So yeah, again, this is a workshop brought to you by Code Labs Academy. It's called Gradient Descent with JAX. So before starting, all right. So before starting, yeah, let me just present myself. My name is Nizim Dib. I'm a data scientist at Code Labs, a data science TA at Code Labs Academy, and I'm an NVIDIA DLI too. So I'm certified by NVIDIA to do like fundamentals of deep learning workshops and transformers workshops. So I have a lot of experience in the field, especially in deep learning. And yeah, I've been picked by Code Labs Academy to perform as a TA in their bootcamps to help organize such workshops for the community. So nice to meet you guys. So before starting into the workshop, I think it's very important to present Code Labs Academy. So the very first question is who we are. So Code Labs Academy is a team of 22 spread members across 8 different countries. And we're currently based in Berlin, in Germany. So basically, we're an international edtech startup that offers technological bootcamps. And yeah, basically these bootcamps are accessible to everyone. And we also provide educational and career advising services. So as long with bootcamp, we also provide educational and career services. And yeah, so our main goal is to help students and non-tech professionals to break into the tech industry. So about our bootcamps, we have many categories. So you can either enroll into an in-person or a remote bootcamp, because we have online bootcamps. So we go into the platform, we have meetings with the students, etc. So yeah, that's pretty intense. And we also have 2 tracks. So you have the part-time track and the full-time track. So for the part-time track, it's going to be pretty soft and pretty light, and it's going to be like a bootcamp across 6 months. But if you want to do like an intense bootcamp, you need to enroll in the full-time option. And of course, if you want to enroll, you don't need any prerequisites, because our bootcamps are exactly made for beginners. So if you want to join the tech community, you just go in there. We will give you some pre-work to do in order to make sure that all the students are on the same base level, and then we can directly start. So yeah, so you may be asking about the financial plan. So we made sure that we offer financial plans that really fits your budget. So before going into that, we have a lot of discounts. So as you can see here, so we have a discount for women in tech. We have a discount in case you're a student. So if you enroll in a group, like you and your friends, or you and your group of friends, you will have discounts. If you pay upfront, you will have another discount. If you enroll from a workshop like this one, so if you're satisfied from the workshop and you decide to enroll, you also have a discount of 10%. And if you're a previous alumni in one of CLA's bootcamps, you can also benefit from like a huge discount in here. So yeah, we offer many discounts, and yeah, you can actually find these in our platform. So I'm going to send you the link of Code Labs Academy in here. So all right, yeah, here it is. So you can go in there and you can find all the details about all the bootcamps. for the financial options, we have two main ones. The first one is the payment in installments. So basically, you split the price of the bootcamp into parts, and then you just start paying like installment by installment. So we have like a really small restriction in here. So basically, you can choose installments as little as 3 and as much as 42 in order to pay. And we also have the income share agreement. So this one is really interesting, especially for students. So basically, you don't pay for the bootcamp until you find a job, okay? And that's really, really interesting for students. So if you're a student, you should consider this one. Now, what about career services? As I said before, we don't only give tech bootcamps, but we also have some specialists that are specialized in giving career services. So, for example, we can take care of your resume and cover letter reviews. So, if you want to enroll into a job, you can get an expert from CLA, and we can discuss with you how to write your best resume. We are going to review it together, etc. We also have portfolio reviews. We have a network of alumni with whom you can network. You can find a lot of opportunities in there. And of course, we will be listed in our jobs and internship listing. What's really interesting, well, I really like this one. So we provide mock interviews. So, basically, if you want to enroll into a job, you need to pass like a programming test, right? It's called a technical interview. So here in CLA, for every single student, we have one mock interview per week in which there is an expert and you in a meeting. The expert is going to give you a problem and you need to solve the problem in that span of time, maybe 14 minutes or 1 hour at max. So this is called a mock interview. It's made to make you adapt to this kind of technical interviews. So that's really interesting. We also have company career fairs, monthly career development workshops, etc. So these are this is for the career services. Now for the bootcamp, we are specialized in 4 techs. So we have the data science bootcamp, we have the UX and UI bootcamp, we have the web development bootcamp, and we have the cybersecurity bootcamp. So me personally, I work on the data science bootcamp. And it's basically the topic of what we are going to see today in the workshop. So without further ado, let's start with JAX. Before going into gradient descent and derivatives, etc., I think it's better if we talk about JAX first. So JAX is a really interesting Python package built by Google, and it's really, really high performance. So basically, the goal of JAX is to accelerate machine learning, all right? And now that we are going to see JAX, you are going to notice that it's so similar to NumPy, all right? So the syntax is basically the same as NumPy. So you can consider JAX as NumPy that is running on accelerators, because JAX is optimized on GPUs and TPUs. So it's like NumPy that is much more accelerated. What's really interesting about JAX, and this is basically what we are going to see today, is that we can build differentiable functions. So you put a function, and then using some JAX classes, you can get the derivative function of that particular function. And that's really, really interesting. And with JAX, we have automatic differentiation. We can have just-in-time compilation, or that's what we call JIT compilation. So basically, you have a function, but instead of executing it like Python does, no, we are going to compile it, save it somewhere, and then we are just going to execute that binary code. And this will make functions much faster. We also have more features like vectorization and parallelization, but we are not going to cover these in this particular workshop. So you may be asking, why using JAX? The very first thing is that you are not going to learn any new API, because if you're a data scientist or if you're a data science student, you must have learned how to use NumPy, right? Because NumPy is pretty essential. So with JAX, you are not going to learn any new API, because as I said before, it's basically NumPy running on accelerators, and you are just going to see that. So many common NumPy programs would run just as well in JAX if you substitute NumPy for jax.numpy. Sorry. So JAX has a NumPy class in there, like a NumPy module, that replaces every single NumPy module, all right? So basically, all you need to do in your code is to replace np dot by jax.numpy. and that's it. Your work is going to be working much faster. And as I said, the same code can run on different backends. So the same code of JAX can run on CPU, and it's the same that's going to run on GPU and TPU. All right. So first of all, let's take a look at how to install JAX. Maybe you would like to install it in order to program with me later, because we are having like a coding part by the end. So it's pretty easy. It's going to get installed the same as any other Python package. So it's pip install JAX, and that's it. All right. And of course, you can use this pip install upgrade JAX in case you already have JAX, but you want to upgrade it. So this is for the upgrade, and this is for the installments. Now let's take a look at JAX versus NumPy. So this is a NumPy code in here that does the dot product between a vector and itself. So it's basically the Euclidean norm squared. So here we import NumPy as NP. We create X, which is np.arrange. We put the start in. We put so this is basically array of numbers. So X is a vector of 1,000 elements, 1,000 number between 0 and 1,000. And here we are going to use the dot product. So it's np dot, and we put X with the transpose of X. And basically that's it. So Mohammed Tawfiq said, hello, can you please share the link for JAX official site in the discussion window panel? Thanks. All right. So it's Google JAX. All right. So here you can find, so this is the repo of JAX, in which you can find tutorials. So there is a source code in there, but you can find tutorials, etc. So of course, it's an open source framework. So yeah, this is for NumPy. Now for JAX, all we have to do is to replace NumPy, but JAX.NumPy, all right? And we are, instead of calling it NP, we are just calling it JNP. So the J is for JAX. And now all we have to do is to replace the NPs by JNPs, all right? So X equal JNP.arrange. We put the same argument inside, and then JNP dot to do the dot product. So it's as simple as this. Let's take a look at another example. For example, we want to plot the sinus function, all right? So we import NumPy as NP, we import matplotlib, then we create linear space. We have here W, which is the cosine of X. So it's the cosine function plotting and not the sinus function plotting. Yeah, sorry. And then we use matplotlib to plot our graph. This is for NumPy. Now for JAX, we do basically the same thing. So we import jax.numpy. So we have only one import here. This is a mistake. So we import jax.numpy, and we import matplotlib, same. And then we replace np by jnp, and it works just fine. So this is pretty awesome. Now here we have a little bit more complicated problem. So here we try to rotate a vector using the rotation matrix. So this is the rotation matrix. We have the cosines in the diagonal, and we have minus sign and sign in here. So the minus is above the diagonal, and the sign, the positive sign, is under the diagonal. And here we are using pi divided by 4. So this is like the angle of the rotation. So yeah, basically we just import numpy and we work with functions. But here we only replace numpy but jnpy, and it just works fine. So this is just a comparison between numpy and JAX. As I said before, JAX does not oblige you to learn any new API. It's basically the same as numpy. It only runs on CPUs and GPUs much faster. So as a summary, all you have to do is to replace np by jnp. That was for a comparison between JAX and numpy. So I think now we should move on. Now let's take a look at some of JAX features. So the first one is the just-in-time compilation. So as I said before, basically, how does Python work? If you define a function in the top of your code, Python is just going to call it whenever, it's going to execute the inside of the function whenever you call it, all right? And it's going to execute it instruction by instruction, because Python is not a compiler, it's an interpreter. But using JAX, what we can do is that we can compile our functions. So when you first call the function, like the very first call, JAX is going to compile it and store it somewhere. And then whenever you call it again, we are not going to execute the function instruction by instruction, but instead we are going to bring the binary code, the compiled code of the function, and we are going to execute it. So it's going to be much faster because JAX has some optimization techniques inside that are going to optimize the function itself. All right. So yeah, so that's for JIT. So JAX allows you to transform your own functions into just-in-time compiled versions using XLA. So XLA is basically the foundation of JAX. And this will increase the computational speed by adding a simple function decorator to your computational functions. So this is a code example. So we import JIT from JAX and we import JNP from NumPy. And this is basically a RealU function. So RealU is an optimization function in neural networks. So basically what it does is that if the input is negative, it's going to return 0. But if the input is positive, it's going to return the input itself. So return x if x is higher than 0, and return 0 if x is lower than 0. So it's not like this. So use jnp.where x greater than 0, x, and then 0. And the thing here is that if you want to use the JIT feature of XLA, you don't need to do anything more than putting a decorator in here. So you just put @JIT, and it's going to be perfectly fine. All right. So this shows how easy is JIT. And again, you're not obliged to learn any new API. So another cool feature is the gradient functions. So as I said before, what's really cool and so personally, this is my favorite thing about JAX. The coolest feature about JAX is that you can have a function, you define a function using Python coding, and then what you can do is that you can use the gradient feature of JAX to return the gradient function itself. And now, whenever you want a derivative of x, all you have to do is to call that gradient function. So let's take a look at an example. Here, we import grad from JAX. So earlier we imported JIT, now we use grad. And we import JNP, of course. And for example, here we have a sigmoid function. So it's 1 divided by 1 plus JNP exponential minus x, all right? And yeah, basically, if you want the derivative of this function, all you have to do is to put a decorator in here and put grad. So it's @grad, and that's it. So in order to train machine learning models, such as neural networks, we need to do backpropagation, which is no more than calculating the gradient of a function with respect to the parameters. So yeah, in backpropagation, all we do is that we calculate the gradient of a function with respect to a certain parameter. So for example, in here, the parameter is x. And JAX offers a super easy API to do this, which is basically you take the function, you put the decorator above it, and that's it. And we are going to make use of it when we implement the gradient descent later on. So now we're done with JAX, and let's start talking about gradient descent. So before going to show you how to implement gradient descent using JAX, I think it's really interesting to understand what is gradient descent first. So let's go back in time, and let's try to figure out how to formulate the gradient descent problem itself. So again, gradient descent is an optimization algorithm that finds the minimum of a function in an iterative process. So basically, we have a function, and what we used to do in school and in high school. So if you want to find the minimum of a function, all you have to do is to put the derivative equal to 0, and you solve the equation. So once you solve the equation, you are going to get all the minimums. But this is not the case always, because when we deal with neural networks, we are dealing with functions with billions and billions of parameters. And calculating, and like solving this equation of the derivative equal to 0 is going to be extremely hard, because you are going to have an equation with billions and billions of parameters. And this is an intractable problem. So what we do, we use a heuristic, basically, and which we call an optimization algorithm. So it's an iterative process. It's an iterative algorithm that is going to find an approximate minimum of the function. And you would be maybe surprised to know that all of deep learning is based on gradient descent in way. All right. So, all right, here I'm going to ask you something. Imagine, so of course, this is the minimum of this function. So it's a square function. So here is the minimum. And let's say that we are here, okay? So the goal is to go to the minimum, all right? If we are here, the goal is to go to the left in order to attain the minimum in here. So what we do is that we draw the tangent line in here. And as you can see here, this tangent line is going down. So the derivative in here is negative, right? If we take another example, for example, here the tangent is going up, which means that the derivative in here is positive. So basically the derivative is the same as the slope of the tangent line, okay? So back here, if I ask you in which direction should I go? Should I go right to reach the minimum, or should I go left to reach the minimum? So I think the answer is pretty obvious. We should go right because the minimum is to the right. So now we can conclude that if the gradient is inferior than 0, if the gradient is positive, which is the slope of the tangent, then we should move to the right in order to attain the minimum. So this is one rule that we are going to keep in mind. In the second example, we are to the right of the minimum, and the gradient is positive because the tangent line is going up. So what we can conclude is that if the gradient is superior than 0, then we should move to the left, okay? So I think I repeat in here. Here I'm trying to formulate the problem of a gradient descent, all right? So we are doing it together. I'm not just going to give you the final formula. We need to formulate it together. So our goal is to reach the minimum. So let's start from a random point. For example, we are here. Now we know that here we are to the left of the minimum point, so we need to go to the right. But we need to make a decision. So how do we do this? We take a look at the slope of the tangent line, which is basically the derivative. And if it is inferior than 0, then we should go to the right. On the other hand, if it is superior than 0, we should go to the left because the minimum is to the left of that random point. Now, for example, if we are here we are already in the minimum, and the derivative is of course equal to 0. So basically what we can say is that if the gradient is equal to 0, then we are in the minimum and we don't need to move at all. Do we have any questions so far? So Michael said, sure, I assume everyone would know this stuff. Maybe we can ask. So, you know, I'm not assuming anything. I'm just supposing that you are all beginners and this is new to you. So that's why I'm asking you. So yeah, if you don't have any questions, I think we should move on. So this was for the direction. So now we can decide in which direction to go in order to find the minimum. So basically, if the gradient is positive, we should go to the left. And if the gradient is negative, we should go to the right. And if the gradient is equal to 0, then we are in the minimum itself. So this was for the case of the directions. Now we have another problem. It's the problem of the step. How big of step should we take? Should we take like a small jump, or should we take a big jump to attain the minimum? So we can actually see this through the gradients, through the concept of gradients. So for example, imagine that we are here in this random point, and we draw the tangent line. So we can see that we are going up, which is pretty logical because we are to the right of the minimum, and the function is increasing. So here the gradient is superior. But take a look at this. If we take another point here, still to the right of the minimum point, we get another tangent line, which is slightly lower than the previous one, but it's still going up, right? So I'm gonna repeat this. If we go further from the minimum, the line is going to go up so fast, so the slope is quite big in here, but here the slope is smaller. So now we can conclude that if the gradient is so big, all right, because here the slope is so big, we need to take a big jump in order to attain the minimum, all right? But if the slope is so small, we need to take a small jump in order to attain the minimum. So now we see that there is some sort of information embedded inside of the gradient concept. So the first one is the direction. We can conclude in which direction should we go. If the gradient is positive, we should go to the left, and if it's negative, we should go to the right. And second, we have the information of the step. So if the gradient is too big, we need to take a big jump, and if the gradient is too small, we need to take a small jump. So now that we have these two concepts, this concept of a direction and the concept of step, now we can formulate the gradient descent. So by using this formulation, x takes x minus learning rate times gradient x, we can kind of summarize all of the concepts earlier. So for example, for the first concept, in the direction, imagine that the gradient x is negative, all right? And you should know that the learning rate is always positive. So this entity in here is always negative because it's a multiplication of positive number by negative number. It gives a negative number. So the entity here is a negative number. And now we have x minus something negative, which means that it's x plus something positive, which means that it's something bigger than x. And now we can say that x is going to move to the right, which is exactly what we said. If the gradient is negative, x should move to the right. And if it's positive, we are going to have x minus something positive times something positive. So this whole entity is positive. So it's basically x minus something positive, which gives me something smaller than x, which means that x is going to the left. So now again, if the gradient is positive, x is going to move to the left. So Mohammed Tawfiq has a question. Hello, how to integrate and deploy the Google JAX program code into the machine learning pipeline process? All right, that's a good question. And you know what? We are just going to implement gradient descent using JAX, and I'm going to show you how to use JAX into building like machine learning stuff. So if you're asking more specifically about machine learning pipeline, I think in the previous workshop we took a look at how to implement linear regression using JAX. And in the next workshop, I'm going to show you how to implement neural networks using JAX. So I think it's the next Saturday. Yeah, so in the next Saturday, we are going to show you how to implement neural networks using JAX. I think you're going to get pretty excited about that. So here, this is the formulation of the gradient descent. So x is the point that we used to see. So this is x in here. LR is learning rate, which is a positive entity. Now, if the learning rate is too big, it means that x is going to have a really big jump. And sometimes it's beneficial because we need to take big jumps to attain the minimum faster. But sometimes, if you take like a really big learning rate, we are going to miss the minimum itself. And that's going to be problematic. And we are going to experiment this later when we implement the code. Now, yeah, and the gradient x is basically the derivative of f with respect to x. And this is exactly the problem in here, because you know, when we do machine learning and deep learning, we are dealing with complex functions, and sometimes the gradients are not that trivial, all right? So with the use of JAX, this part is going to be pretty easy because it's just going to be a function, a Python function, all right? So if we don't have any more questions about gradient descent and JAX, I think we should start coding. You should go to, do you want to code with me? Because I'm going to code gradient descent. So it would be really interesting if you go to your computers and start coding gradient descent with me using JAX. All right. So yeah, like in any Python project, what we need to do first is to import our libraries. So the most important library here is JAX. So yeah, we are going to import JAX first, and from JAX we'll import JAX.numpy as J and P. So the first one is to import JAX, the second one is to import NumPy from JAX. Now what we need is matplotlib. So import matplotlib.pyplot as PLT. So this is a library that we are going to use in order to plot the results. So if you ever need something else, we are just going to come back here and add all the stuff. So the first thing that we are going to code is our function. So I prepared a really beautiful function. So a function that's going to be really beneficial. So here it is. So we're just going to call it fx. So this is the formula of the function. We can make use of it. So as you can see here, we're not using any JAX. All right, it's so Pythonic in here. So it's basically a polynomial. So it's t to the power of 4, t to the power of 3, t to the power of 2, and t is just a translation of x. So let's try it out. So if I give 2 to f, it's going to return 3. If I give 5, it's going to return this, etc. So the first task, the first thing that we are going to do in this code is to plot the function. So we need a plotting function, all right? So to do this in Python, there's a really cool way. It's using linear spaces. So we are going to use JNP. So it's line space. I'm going to put 0.5 in here, 10 in here, and let's say that we need 10,000 elements. So basically, this is going to be a vector. All right. So this is going to be a vector of size 10,000 that contains elements, that contains number between 0, 5, and 10. All right. So it's like we are covering the whole linear space in there. Now what we need to do is to put y equal to fx. So basically, for every single number from x, we are going to apply the function f. Okay. Now, if I print y, it's going to give me this big vector. Now that I have this, what I can do is to call plt.plot, and we are going to put x and y in here, and it's going to give me this cool function. Now, what I can do is to change the figure size. So maybe we should work with something like this: figure size equal to, let's try 5 maybe. All right, let's try 6 7. All right, so this is our function. As you can see here, we have two minimums. We have one global minimum, which is like the most extreme minimum of the function, and we have the local minimum in here, which is still a minimum, but it's not the most extreme one. Like there's still a point that is lower than that. So yeah, this is our function. Now to make it more professional, let's create a function. I'm going to call it plot results, maybe. Results. And it's going to take f as an argument. What we might also need is to plot points, because we are going to plot all the updates of x. So maybe before creating the function, we need to add this feature. Well, let's just put it in here. So we have points. So if you do have points, what we need to do is basically this. So let's call it point x is equal to point 0 and point y. And then we have plt.scatter, and we are going to scatter. So these are the x coordinates of the points, and these are the y coordinates of the points. So let's try it out. So plot function f, and we are going to give it these points. So 2, 4, 3. Oops. 3, and we have 1, 5, 6. Okay, so we should put both lists into a list and pass it to the function. So as you can see here, we have our function, we have the graph of the function, and yeah, we have the 3 points in here. So maybe we should use a different color. So to use a different color in Matplotlib, just type in C, which stands for color, and give it something else. So red. So the points should be displayed by red. Okay. So now my plotting function is ready. Now what I need to do, maybe it's time to start coding the gradient descent itself. So yeah, let's just put the title in here. So gradient descent. All right. And yeah, so here we are going to use, so we are going to, oops, no. So we are going to use the gradients feature of JAX. Okay. So we are going to create a new function. We are just going to call it gradient of f. So it's grad f, and it's going to be JAX dot grad, and we put f in here. All right. So this function is now the derivative of f. It's so basically grad f. So grad f of x is equal to f prime of x. All right. So grad f is literally the derivative of f, and this is one peculiar feature about JAX, because no other framework can do this actually. So now it's so easy. Now maybe it's interesting if you can plot this function. So what if I do this? Define scale output, head shape. What we can do is jax.map. All right. So we have like this. Oops. Now I think we can plot this. So if we do plot of x. All right, cool. So basically this is the derivative of f. This is f prime, okay? And this is literally the derivative of the first function. So that's really cool. Now we must make use of this actually. So yeah. Now we start by, so this is the hardest part about gradient descent. So this is called the training loop. So now we are going to work on the training loop. So what we need first is to define our learning rate. So as I said, it's positive entity and it should be small, like this. So maybe that's too small. Let's put it like this. And then we need to define a distance function. So I'm just going to use a lambda function in here. So it's lambda xy, and it's going to return the absolute difference. So it's jnp.abs. So abs stands for absolute. There's no return in here. And it's going to be x minus y. So here, this lambda function is going to return the absolute difference between x and y, such as x and y are two consecutive steps in the learning algorithm, in the training loop. So we are going to see this right now. And we should also define a threshold. So it's like, so this threshold is going to be used as criteria to stop the iterative loop. Because, you know, in gradient descent, you are going to use a loop, and there must be a condition to stop the loop. So the condition is going to be, if the distance is bigger than the threshold, then yeah, keep going, keep updating the x's. But if the distance is smaller than the threshold, then you should stop the loop. So now we are going to define something like this. So we are going to define xn and xn plus 1. All right. So xn is going to be replaced by xn like this, and xn plus 1, I'm going to refer to it by xn1 like this. Okay, because you can't put plus in the variable. So let's put xn is equal to something really large to just not saturate the loop. And now xn plus is going to be our initial point. And let's, for example, start in 1.5. Okay. Now we need to store, I would like to store all the points, all the updates, so that we can plot them. So like this. And we have y in here. So maybe it's better if we can store the very first values like this. So we are going to store this, and we are going to store this. So x is for the points themselves, and y is for like the function applied on that particular point. So, all right. Are you with me, guys? Am I going too fast? Should I go a little bit slower? All right, there you said it's okay. Is it the same case for you guys? All right, I'm assuming that yes. So, okay, now that we defined the initial step, so we have the linear rate, we have the distance function, we have the threshold, and we have our 2 points, so xn plus 1 and xn. So let's just, maybe it's better if we do it like this. All right, now we create our training loop. So while the distance between xn and xn plus 1 is larger than the threshold, then, so here I think I should formulate the problem. So in gradient descent, what we basically do is this. X of n plus 1 receives x of n minus the learning rates times the gradients of, or basically it's f prime of xn, all right? And then xn is going to receive xn plus 1. So this is how it's done, okay? So now what we do first is to update xn because we are going to use it later. And then we are going to use this formulation in here. So it's xn plus 1 is going to receive xn minus the learning rate LR times f prime of x, but we don't have f prime. So here we are going to use a grad function that we extracted using JAX. So here grad f is going to be used. So xn minus learning rate times gradient f. And yeah, so we are going to pass our xn in here. And yeah, that's it for gradient descent. So what's left is that we should store our points. So we are going to store xn plus 1. And we are going to store the f, so the function applied on xn plus 1. And now it should be working. So maybe you should use a variable here that we are going to call steps. So it's initialized at 0. And then in each step, we are going to increment it. And by the end, we are going to print out the number of steps. So we are going to print number of steps. It's going to be steps. So now if I run this, yeah, so the number of steps is 144. So now we should visualize the update of x's. So we are going to use this plot function. So it's called plot results. So I'm going to pass the function f, and I'm going to pass a list of my points. So it's points x and points y. And now, so apparently we have a problem in here. So this is f. I think it's inverted. So yeah, here we should have 1. Okay, good. And now, all right. So as you can see here, these are the updates of my point. So we started in here, and it kept getting down and down and down. It's like a ball. It's like we are rolling a ball into a hill. So we started in here. Maybe I should zoom in more. So we started in here, and it kept going down and down and down until we reached the minimum. So this is with the learning rate of 0.01. So maybe if we take a slightly bigger rate, 0.02, we are going to only use 80 steps compared to what we used earlier, which was 144. So now we should, so logically, yeah, as you can see here, the pole seems to be faster, seems to be going down faster. So we started here, and then we took a big jump, and then a smaller one, and then a smaller one, until we reach the minimum here. Okay? So is it clear, guys? Should I repeat explaining the code? All right. Now let's experiment something else. Let's say that we start from here. So for example, we start from the 0.9. Let's take a look at this. So if we start from the 0.9, yeah, it should be 9.0. 9 point. So yeah, if you start from 9, we are going to take 90 and 8 steps, and it's going to be like this. So we started from here, and this is where we get stuck, because this is like the closest minimum, all right? So we take a big jump, and then a bigger jump, etc., etc. If we take a smaller learning rate, so for example, like this, the algorithm is going to take longer. So we are talking, because we are taking small steps. So it's pretty logical that we are going to take more steps. So here we took 310 steps. And as you can see here, the steps are really, really small. All right. So what happens if, for example, I use a learning rate of 0.05? What do you think would happen, guys? All right. So what basically happens is that we are going to take some really large steps, and we can totally miss this. So we are going to experiment with this. We are going to run the algorithm. So only 43 steps. And if we plot, we can see that the first one was a really big step, but it wasn't enough to totally escape this. So let's take a larger one. Let's take 0.07, and we run it. And we take a look. So it's an even bigger step, but we couldn't escape the local minimum. So for example, if I use 0.1, and if I take a look, so yeah, it's like literally we jumped right through the local minimum. And yeah, let's take like a slightly bigger one. So, all right, so here something happened. Here we jumped a little bit further than the local minimum, but then we came back. So we jumped from here to here, and then we started coming back a little bit. So what I want to experiment is having this. Take a look at this. So here we took a really big jump. So we jumped from here to here, and then again we started sliding down into the local minimum. So I need to get something a little bit bigger, and take a look at this. So this is a little bit special. So basically what we did is that we jumped from here to here, and then instead of rolling back into the local minimum, we rolled to the left into the global minimum. So this is maybe one of the benefits of having a big learning step. So here we successfully reached the global minimum. Now, if we take like a much bigger learning rate, for example, 0.5, like this. Probably. Here we totally jumped into the global minimum, etc. All right. So what I was trying to explain is that yeah, I'm not using any plugins. So it's basically Jupyter Notebook in VS Code. Okay. So you download it like this. You go in here in the extensions window, and you type in Jupyter, and you have it like the first one. So by having that, you can open files like IPython notebooks into this format, and you can work on them. So basically that's it. Otherwise, I'm just using JAX and Matplotlib to do this. So this is an implementation of gradient descent. Any other questions? All right. So we are going to have an article about gradient descent with JAX in our webpage. So all the code is going to be in there. You can just copy paste it and run it on your site. So all you have to do is to first download JAX as I showed you. So it's pip install JAX, and that's it. All right, if you don't have any other questions, we should call it a day. Thank you guys for joining. It was a pleasure. And yeah, you can find all the code in the article later on.